Okay, here we go. Up and running. When last I left you on the hydrolysis worksheet, we were on page 36. And I hope I'm talking loudly enough because I'm right beside, I'm doing this from the book room because it's one of the only places I won't be interrupted, and I need to mute that, but I don't want to bother Mr. Weinberg's class, so I'm going to try and talk quietly and yet close to the microphone. So here we are. When last we left, we had just done the bottom example, last example on page 36. And I did want to draw your attention to it because over here, I had done it correctly. I said SR2 plus, it's not one of the feel creepy ones, and so it does not hydrolyze. And I said, yes, does NO2 hydrolyze? Yes, because it has a weak conjugate acid. But over here in the actual handout, it says HNO2 is strong. Well, that's not right at all. So you can just change that to weak. Okay. All right. Now, common error alert. So this is something that students do wrong. Many students think that when an ion hydrolyzes, and if you remember hydrolysis is the reaction of something plus something. See if you can think of those two things. It is the reaction of an ion plus water. Okay? And many students think that because we form, when that ion reacts with water, they look and they say, I have made a weak acid. And they say, well, therefore, my solution must be acidic. But that is absolutely 100% wrong. Okay, the solution is not acidic because it doesn't matter that we have made a weak acid. What matters in terms of whether a solution is acidic or basic is the concentration of the H plus compared to the concentration of the OH minus. And in this situation, we have made, OH minus has been made. And so the concentration of OH minus is going to be bigger than the concentration of H plus, which was not made. And so therefore the solution is going to be basic. Another way to look at this is that every single Bronsted-Lowry acid-base equilibrium has an acid on both sides and a base on both sides. So no matter what, you're always going to have an acid in your products. So it doesn't matter. You won't be able to tell whether you have an acidic or basic solution by whether you have an acid in the product, because there's an acid everywhere. There's an acid in the product, there's an acid in the reactant, there's a base in the product, there's a base in the reactant. It just doesn't work. So you need to look instead for the H plus and the OH minus, and that's the only way that you can tell. Okay, so here's another example here. We have ammonium. Okay, here is our ammonium. It is a cation. Okay, and I don't know if you remember, but cationic hydrolysis is always acidic hydrolysis. You don't have to memorize that because, you can look at it and go, well, NH4 plus can accept a proton and become NH5 plus. Not plus, but 2 plus. That looks ridiculous, right? That's like some bizarre thing we've never seen before. On the other hand, it's perfectly capable of giving away a hydrogen and becoming a base. Now remember, we're not looking at did it make a base or did it make an acid, because this reaction made both a base and an acid. So we need to look, did it make hydrogen or hydroxide? And we won't actually see hydrogen here, so I shouldn't write that. I should write H3O plus or hydroxide. And in this case, we have H3O plus. And if we have H3O plus, that means our solution is acidic. So don't make that mistake. Don't say, oh, I made a base, it must be basic. No, no, no. Look for hydronium or hydroxide. Okay? Amphiprotic ions. Now, if you recall, amphiprotic ions, those are ions that have an H and they have a negative charge, so these will always be your anions, okay, because they have that negative charge, but they are anions that have that H. So let's look at our salt, and remember, a salt is just an ionic compound, okay? It dissociates into the cation and the anion. You're never going to have it dissociate into three things. So once you have your cation, everything else is going to be the anion. Everything else is going to be a polyatomic ion if there's more than one thing. Okay, so you can just look and say, there's my cation. All the rest of the stuff has to be the anion. Now, we know that sodium will not hydrolyze. How do we know that? Do you remember? The only four cations that hydrolyze are, do you remember the four? Ammonium, NH4 plus, ammonium. And the other three are Fe, Al, and Cr, and all of those are 3 plus, 3 plus, 3 plus. And if you don't remember my weird little mnemonic for this, it's a weird little mnemonic because it spells kind of feel and then creepy. Okay, I don't know, it's not the best mnemonic in the world, but it helps me remember it, and maybe it'll help you remember it as well. Okay, and there are three of them, so that's why they have the 3 plus charge. Ooh, look, I never thought of that before. That's a new one. Okay, so Na plus will not hydrolyze because it is neither NH4 nor is it one of those three metals. So cation will not hydrolyze. However, our anion has both an H and a negative charge. Therefore, it can act as a base by accepting a proton, right? Grabs a proton from water and becomes H2CO3, and it produces OH minus. And we look and we say, would that be, if that was the only thing I was thinking of, this would be basic, okay? If we only had that to worry about. However, HCO3 also has that hydrogen, and so it can also donate a proton. It can both accept a proton and donate a proton because it is amphiprotic. And so it can act as an acid. So it will now give its proton to water. And we end up with CO32 minus and H3O plus. And again, don't look at this one. Nope, 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 nope. Okay, you want to look at either hydroxide or hydronium. And if you look at hydronium, then the solution is acidic. And now we have a problem because the solution is basic, but the solution is acidic. Well, what is it going to be? And the temptation is to say neutral, because you have basic and acidic. And in reality, some of the hydronium will neutralize some of the hydroxide, but one of these reactions happens more than the other. And whichever one happens the most will be the one that determines whether it is basic or acidic. Okay, so HCO3 does both. It makes both basic and acidic, but one of the reactions happens more than the other. But it does one of these reactions more than the other. Okay, that does make sense. That's good. Okay, so we have to ask ourselves, is HCO better as an acid, or is it better at acting as a base? And the way we can tell that is we can look at the Ka and the Kb of HCO3. So that's really straightforward for Ka. We simply go to our data booklet and we look up HCO3. That is down here somewhere near the bottom-ish. Oh, there it is. HCO3 minus. This is acting as an acid, so we're looking up its Ka, and that's 5.6 times 10 to the negative 11. Okay, so that's what we've written here. Just look it up. Now you remember KBs. We cannot just look up a KB. We have to do the calculation where KB is equal to KW over Ka of the conjugate acid. Who is the conjugate acid of HCO3 minus? Who is the conjugate acid of HCO3 minus? Conjugate acid is H2CO3. Add an H and add a plus, you end up with two H's and a neutral molecule. So to calculate our Kb, we are going to take Kw, 1.0 times 10 to the negative 14, and we're going to go look up Ka for H2CO3. Okay, so we're not down here anymore. This was when we were looking at HCO3 as an acid. Now we're saying what's the Kb of HCO3. And so if we're looking for our Kb, we want HCO3 to be acting as a base. And so then we can find the Ka of H2CO3, 4.3 times 10 to the minus 7. There it is, 4.3 times 10 to the minus 7. We do the math, and we get 2.3 times 10 to the minus 8. So that's our Kb, and there's our Ka up there. If you look at these two values, do you think that HCO3 is better at acting as an acid or better at acting as a base? Hopefully, you look at this and you say, oh, 10 to the negative 8, that's bigger than 10 to the negative 11. So we can write this statement. And if this is a written response where they ask you to justify your answer, what that would mean is you would do these calculations. And you're going to make this comparison. Justify your answer. Okay, so if you are justifying your answer in a written response question, you're going to want to do the actual writing down of the Ka value, showing the formula for Kb, showing the plugging in of the formula values into the formula, and showing the calculation of Kb, and then doing the comparison. So in this case, our Kb was bigger, so it produces a basic solution. Not that the acid one doesn't happen, it just happens less. And so the predominant or main reaction is the one where HCO3 acts as a base, and it produces a basic solution. So that's for a written response. That's what you're going to want to do. Okay? Let's try another one, just because this always seems to be something that people need more practice with. Here is a big, huge, nasty formula, which is why you're going to be glad I've typed this out for you. We have Li2H2C6H5O7. Dear goodness, where does, what am I going to do with that? How does that split apart? Well, if I look at this, here is a metal, and my metal has to be my cation. That means that everything else is my anion. And I believe this is actually the dihydrogen citrate ion, I'm guessing. Dihydrogen citrate. Certainly don't expect you to know that, but you can go and look up H2C6H5O7 on your data booklet. And it should be a pretty big formula, so it shouldn't be too bad to find. Oh, there's an H3C6H5O7, so somewhere down below it, I should find an H2. Here it is here. Here's my H2C6H5O7 acting as an acid. Up here, I'll erase all the other stuff so it doesn't clutter it up. Up here, we have H2C6H5O7 acting as a base. You can see it's got those hydrogens and it's got the negative charges, so it is, what's the word? Amphiprotic. Okay, and while I'm here, I'm going to grab its Ka value because I'm going to need it, 1.7 times 10 to the minus 5, although actually, I think I have it here already. Okay, so you're going to ask yourself, once you have split your ions apart, you're going to say, does the cation analyze and does the anion hydrolyze? I don't think it said hydrolyze last time, but that's okay. Lithium does not hydrolyze. Why not? It is a cation, and only 4 hydrolyze. And those 4 are ammonium, H4 plus. And who are the 3 metals? The Al, crazy, and what's their charge? There are 3 of them, so each of their charges is 3 plus. Okay, so it's none of those, so it won't hydrolyze. Now, we just looked at our anion, the dihydrogen citrate ion, on the chart, and it has both that H plus and its O and a minus, and therefore it is amphiprotic. And so we are going to have to write both possible hydrolyses equations. Hydrolysis. So first of all, here we have it acting as a base, accepting a proton from water. Okay, so we end up with H3, C6H5O7. And we are left with hydroxide. Now we know that we're going to have to do an acid, so we might as well calculate our Kb here. How do I know I'm calculating Kb? If OH is a product, you'll be using Kb, not Ka. Okay? And that's, of course, for weak ones. For strong bases, you don't need that because you don't, like, they don't have a K, they just go to completion, right? But for any weak base, it's going to produce hydroxide, and you're going to use a Kb. So here's our Kb. We're going to do Kw over Ka of the conjugate acid. You'll notice we've added a hydrogen there. We started with H2, and now we have H3. And we picked that value off the table for H3, C6H5O7, and we do our calculation, and we get 10 to the negative 11, 1.4 times 10 to the negative 11. Our second hydrolysis equation, whoa, that was fun. Our second hydrolysis equation is as follows. Now, last time H2C6H5O7 acted as a base, now it's going to act as an acid, and it is going to give its proton to water. So now water has that extra proton and it's become H3O plus, and this guy now has only one hydrogen, not two hydrogens. Okay, and since this was acting as an acid, we made H3O plus, and if we make H3O plus, H3O plus is the product, you're going to use Ka. Okay, and that one we can just look up, and that is 1.7 times 10 to the minus 5. So let's now compare our Kb. This was our Kb. You can see that's our Kb. We just kind of lost track of it over there. Here is our Kb, and here is our Ka, and those are both of the dihydrogen citrate ion. You can see that Ka is bigger than Kb. We have 10 to the minus 5, which is bigger than 10 to the minus 11. So this solution, since Ka is greater than Kb, the solution will be acidic, and our predominant reaction will be the acidic hydrolysis that produces H3O plus. Okay. Now, other ways you could compare the strength of the acid or base if the question is multiple choice. So this is for your multiple choice section, or if you're just doing things very quickly as a part of another question, or if it doesn't ask you to justify your answer. You can approximate your Kb using only the powers of 10 and ignoring the rest. So when we had, like that keeps doing that on me, that's crazy. So when we had, when we were finding the Kb of HCO3, remember this is the Ka of who? H2CO3, the conjugate acid of our substance we're finding the Kb for, and of course that right there is Kw. You can just ignore the front part of the number, yes, and you can say, I'm just going to look at my 10 to the 14 and my 10 to the negative 7, and when I divide those two, I get 10 to the negative 7. So my Kb is approximately equal to 10 to the negative 7. Our actual Kb is 2.3 times 10 to the minus 8. So these aren't really that close. However, what if we start comparing it to the Ka? Well, the Ka is 5.6 times 10 to the negative 11. So it doesn't matter actually whether we're dealing with a negative 7 or whether we're dealing with a negative 8. Both of those are going to be greater than 10 to the negative 11. So this is going to be basic. Okay? Do not use this method on long answer questions if you are asked to show your work or if you're asked to justify your answer. If they're just like write the predominant reaction and it's only worth like 1 mark, then you go just right ahead and just pick which one and write it. So be smart about what you're reading in the question and how many marks it's worth. Okay, so the other way of doing it is that you can figure out which is stronger by its position on the Ka table. So we're going to start with the 2 ions that we had worked with before, and one of them was that carbonate ion. And in fact, I'm going to back out on this so you can see the whole table. Okay, there's our whole table. And this right here is our HCO3, and this right here is our HCO3. Okay, so you can see from where they are, this HOCO3 is kind of in the middle-ish of the table. So it is a middling strength as a base. Middling strength as a base. HCO3 on the acid side of the table, on the left-hand side of the table, is way down at the bottom. I mean, it's even like almost touching the word weak. Yes? So it is on the weaker end of weak acids. So it's a weaker weak acid, and it's a middling weak base. So therefore, HCO3 would be a better base. It says that down below. HCO3 minus is a better base than it is an acid. So I don't know why I would write it again, but you know me, I write things 17 times. All right, and we're going to do the same thing for the dihydrogen citrate ion, the other one, amphiprotic ion we looked at. You can just look on your table and you can say, this dihydrogen citrate here is, oh, I don't know, is that about like the lower quarter or the lower third? Yes? Whereas H2CO3, the dihydrogen citrate ion over here, is kind of more in the middle. So this is on the weaker end of the weak bases. This is on the middle end of the weak acids. So it's going to be a stronger acid than it is a base. And so the predominant reaction will be the acidic hydrolysis. So if you're doing a multiple choice and you feel good doing that, that's fantastic. Okay? All right. In a multiple choice question also, you don't always need to write out the dissociation equation just to decide the pH. However, I'm going to recommend that for now you write the dissociation equation until you're really good at just, when you see calcium bromide in your mind, if it immediately separates itself into Ca2 plus and Br2 minus, then you don't need to write the dissociation equation unless it's asked for. But if you are not able, like, if you've done this for a long time, like say, 30 years, like I have, there's no way that I can't, this just pops up in my head, okay? It has mapped, there's so many neurons involved in that, that's just what pops up. But it might not pop up for you yet because you've been doing it for what, like maybe a year and a half dissociations, and who knows if you understood it last year, right? So anyway, do write your dissociations until you are automatic at predicting what those ions are going to be. So what if neither ion hydrolyzes? Remember, calcium will not hydrolyze because it is not NH4 or FeAlCr. And so calcium does not hydrolyze. And remember, when we are looking at our anion, we are going to look at whether its conjugate acid, which is HBr, and we're going to ask, is it strong or is it weak? If it is weak, we would have hydrolysis. And if it is strong, we would have no hydrolysis. And in this case, HBr is strong. We don't have weak one, so there is no hydrolysis. So calcium does not hydrolyze, bromide does not hydrolyze. And so if you're asked what the pH is of this solution, that's going to be pH of 7. Okay, and that's of course neutral. So that is a neutral salt. CaBr2 is a neutral salt. And you wouldn't have to write down anything to solve a problem like that in a multiple choice. You'd just be like, CaBr doesn't hydrolyze, neutral, 7. However, if you've got some amphiprotic ions, definitely you're going to want to be writing something down. And if you have a situation like this, where we have NH4Cn, who's your cation? Ammonium. That means your anion is the Cn. We ask ourselves, does the cation hydrolyze? And yes, it is one of ammonium or L-creepy, and it is the ammonium part of that. And if we write the hydrolysis reaction, remember cations always produce, it's always acidic hydrolysis because we are producing H3O plus. Does CN minus hydrolyze? We ask ourselves, is the conjugate acid of HCN weak? Because if it's weak, it will hydrolyze. Yes, so CN minus also hydrolyzes. And we're just going to do a quick check and say, is it amphiprotic? And the answer is no, it's not. So it's only going to do basic hydrolysis. Anions do basic hydrolysis unless they're amphiprotic, in which case they do basic hydrolysis and acid hydrolysis. So does it hydrolyze? Yes, it does. And we end up getting OH minus. So again, we have a mixture of both. The hydronium coming from the cation, the hydroxide coming from the anion. Because both of them hydrolyze, again, we're going to do the same thing we did with an amphiprotic ion. We're going to compare the Ka and the Kb. And so we have, let's see, we have H3O plus being formed. So are we going to use a Ka or a Kb? We're going to use a Ka. Okay, so we produced H3O plus. We just looked that up on our table, and it's 5.6 times 10 to the minus 10. For the Cn minus, we produced OH minus, and when we produce OH minus, we are going to use Kb. And we cannot just, what am I trying to say? You can't just look it up on the table. This is Kw over Ka of the conjugate acid HCN, which I should have written, but I didn't. And we get 5 times 10 to the minus 5. Who's bigger? Kb is bigger. So since Kb is bigger than Ka, the solution will be basic. Anything else on here? So if both ions hydrolyze, compare the Ka of cation with Kb of the anion. Okay, good, that's what we did. For each of the following, now we're down to the questions. You're going to write the dissociation. You are going to decide if none, either, or both of the ions hydrolyze, and then you are going to, let's see, check to see if the anion is amphiprotic. Does it have an H and a negative? And you're going to write all the hydrolysis reactions. If there's only going to be one most of the time, but if you have an amphiprotic one, there will be 2. If you have a cation and anion both hydrolyze, you will have 2 hydrolysis reactions. I will never give you a cation that hydrolyzes and an amphiprotic anion. That would be crazy. Okay? If the anion was amphiprotic, calculate its Kb. Compare Ka to Kb. If both the cation and anion hydrolyze, calculate the Kb of the anion, the one that made the hydroxide, and compare the Ka to the Kb. Then you're going to finally state if the pH is greater than, less than, or equal to 7, and if that makes the solution acidic, basic, or neutral. And I had intended these to be like you do it in class and then we look at it together, but you could do them kind of like a little problem set here. The answers are on the next page, so you can check those out, and I will leave it there for today, and if you have any questions, you can ask me about it. Thank you very much.